Okay, so I'd like then to start. I'd like to welcome everyone in here. Thank you for joining us. This is the second event actually where we're showcasing the great things that our faculty are doing. We wanted to use this vehicle not only to let our other faculty know, but also our alumni and the community just to see some of the things we're doing. So today I'm really very excited because we're going to hear about this new concept, LoboDrome, and I'm really looking forward to finding out what is it all about and learning more about it. So with that, I want to first thank all those who joined from outside UNM, but also inside UNM. And I want to thank ahead of time all our speakers today, so and all the presenters. Thank you. And with that, I will let Mariah take the helm.
Thank you, Dean Christodoulou. Good afternoon, everybody. My name is Mariah Pauchili. I'm a senior here at the University of New Mexico studying chemical engineering. Like Dean Christodoulou said, thank you, everybody, for being here. So it's my pleasure today to be the host for today's Engineering Action Speaker Series on how drones are used in research and the plans for an on-campus outdoor netted drone facility. Although many faculty members at the school use drones in their research, today we are going to hear from some of our students, along with Rafael Fierro, who is the Professor of Electrical and Computer Engineering, Fernando Moreau, Assistant Professor of Civil Construction and Environmental Engineering, and Xiang Sun, who is the Assistant Professor of Electrical and Computer Engineering. Before we get started, I would like to mention that we do have a time reserved at the end for any questions and answers. So I encourage you to use the chat function for your questions. It is now my pleasure to introduce Dr. Rafael Fierro.
Well, good afternoon, everyone. I am really happy to be here and be starting this exciting meeting. I'm going to share my screen. And start my presentation. Can you see my presentation?
Yes.
Okay, so again, thanks for the introduction, Mariah. I am going to talk about the research that we are doing at the Marges Lab, which is the multi-agent robotics and heterogeneous systems, and also mention this idea, this initiative, the LoboDrome. The first thing that I like to do is to acknowledge our sponsors. The research in my lab has been supported by the Department of Defense, the Army Reserve Office, the Air Force Research Labs, Sandia National Labs, the National Science Foundation. I was told that I have 2 minutes to tell you what I am doing, what we are doing, and but then I was thinking that well, how I can show you what we have been doing in the last 10 years, right? So it has been 10 years, very exciting time. And I decided to just put in one slide, hopefully it's not too chaotic or crowded, just to tell you some of the projects that we are working on. But the first thing that I like to say is that I am fortunate to have such a wonderful collaborators. My colleagues at UNM, Dr. Melanie Moses, Dr. Lydia Tapia, Dr. Poroseva, Dr. Miko Oishi, have been working with us and in different projects. So I am really grateful for their support, and we hope to collaborate, to continue our collaboration. So we have been doing aerial robotics, transportation, suspended load transportation, and many other type of projects. Projects funded by different agencies. For instance, for a project that was funded by the Army is about how to exploit heterogeneity. Is given. I have this image here, this figure at the bottom left of your screen. So that is an example of how drones can collaborate with ground robots in order to accomplish a mission. Also, with the collaboration with Dr. Tapia and her student, Dr. Alexandra Foss, now at Google, we developed a very nice framework for area suspended loads. Even before Amazon, before other companies publicized this idea of delivery, we were flying on campus. However, due to the restrictions, we cannot fly on campus anymore, and we are confined to this small room in the basement to fly the drones, as you can see this video running at the bottom right. Recent projects include the support by Sandia National Labs, and that includes a project that how to prevent that malicious UAVs or malicious aerial robots may enter a critical or protected area. So with we are working with Dr. David Novick, and this project is in its second year, and we will be working with Dave until 2022. Well, hopefully we can continue working. A new project that is going to be official in the next few days. It's a project with Dr. Steve Burger at Sandia National Labs. It's about airborne manipulation. So again, we are very excited about this project. We will be working for 3 years and try to develop the foundations for aerial manipulation. And I have my students as well. Some of them are working in companies, others are doing PhDs, others are professors, like for instance, Professor Nicola Bezzo, Professor Patricio Cruz, Professor Jonathan West, Ivan Palunko. So those my students are actually continue their academic careers in universities. Finally, I like to see a vision of the future. So I have my students, my current students, my postdoc, Afroza Turin. I have 3 PhD students, Jean, Lashmi, and Avi, and master students, also Isaac, Michael, Mark, Daniel is a bachelor in mechanical engineering, and Zane. This afternoon, you are going to hear from Isaac. He's going to talk about our counter US project with Sandia National Lab. And you are going to also hear from John Erickson, and he is going to discuss this new project, this very nice, fantastic project, leader being that Professor Moser is the leader, is the PI, it's a volcano monitoring. So John is going to tell us more about that project. And with that, I'd like to thank you for your attention. And I have 1 minute video so you can see what we do in my lab. Thank you again. Mariah, do we have time for a question? Or in case there is any?
I think we want to maybe hold them for the end. Yeah.
Okay.
Is it, am I turned okay? Okay, share my screen. Can everybody see that?
Yes.
Okay. Okay, hi everybody. My name is Isaac Sessler. As you heard, I am working on the Mobile Adaptive Reactive Counter Unmanned Systems project here at UNM, or Marcus. And we are sponsored by NATO, Sandia, the Swiss Army, and yeah. Okay, so let me get a little overview here of what we're trying to do. So let's say we have an airspace, as Dr. Fierro said, that we want to protect from threats such as aerial drones. You know, and we don't want any like malicious drones coming in, taking pictures or something like that, obstructing airspace. So how do we go about preventing that? So the Marcus program aims to focus on the detection, tracking of these drones, and then using our drones to then capture these threat UAVs. Okay, so here's a little overview of the proposed work. So we have different platforms. We have a mobile platform, as you can see off to the right, and a ground platform. On these platforms, we'll have different sensing, such as radar, acoustic, LiDAR, and as well as having a neutralization payload on board. We'll also have a base station, which will integrate these different detection methods, and so we can get an accurate position of where the drone is in space. And this base station is also going to generate a intercept course. Okay, so let's go down a little bit. So detection of drones requires a trained machine learning model, which was done using something from all these pictures from DroneNet. As you can see here, each of these pictures has a bounding box as well as a label. This is just a small subset of the pictures used, but really what was used to train this model was upwards of 1,000 or so images. So using this, we got to train the model with about 96% accuracy to detect drones. This was all done via TensorFlow and SSD-based model architecture. And so now I'd like to switch gears a little bit and talk a little bit about what runtime assurance is. Okay, so runtime assurance gives us the ability to use an unverified controller to make decisions about how our quadrotor should behave. So something, like an unverified controller isn't the best idea when you want to preserve hardware. You know, something may work in simulation, but when you transfer it over to the real world, just because it worked in simulation doesn't mean it's going to work. So you have a strange gust of wind, you have a smudge on the camera lens, you have a fluctuation in magnetic currents or something like that that's going to throw the compasses awry. You know, we want something that's going to keep our hardware safe. So to counter this, we have a decision module observing the outcome of each of these controllers. So quickly, we have the decision module, which knows the state of the quadrotor. With this, it knows both the external state and what's going on internally. And with this information, it can then use a unverified controller if we're in, for example, an open space, or if something happens, something strange goes wrong with the compass or something like that, we can then use a verified controller to make decisions for us. Then the decision module will then give actuated commands. So, okay, why are we running runtime assurance for Marcus? So this allows for an easy transfer from simulation to hardware. You know, we're not going to damage any equipment. You know, and like I said, if something goes awry, we have a safe controller that can take control and get our test equipment to safety. So at UNM right now, we're going to be using the runtime assurance as a active object avoidance. And also, you know, something to add, this also will simplify things because we can then have several students working on something. You know, I can be working on the framework. We can have other students working on a performance controller, which I mentioned here, which focuses on getting the threat UAV as fast as possible. Somebody else working on a safe controller, which focuses on object avoidance and keeping equipment undamaged. And runtime assurance can then, you know, the person who made the performance controller doesn't have to worry about anything getting in the way or wrecking hardware because we have a decision module which will take care of that. Okay, so here's a little bit of our hardware. Up in the top left corner, the top left picture, and down here we have, this is what it takes to build a quadrotor. In the bottom right corner of this picture, we have really the brains of the quadrotor. We have the onboard computer, we have the flight controller, we have the stereo camera. At the bottom, we have a fully assembled quadrotor. This is one that we have built at the moment. We are going to have several others built. This is more of our test platform right now. And then at the top right, you can see our lab. So you will see these red cameras up top. This is our motion tracking system. Since we're confined to the basement, we can't be using GPS, and it just doesn't work very well. And so in these pictures, you'll be able to see the Vicon tracking balls. And okay, then here's our future plans. We want to enhance our object detection. We want different software frameworks so we have it more, so we're able to distribute this platform a little easier. We want to start testing outdoors, test drone detection, as also we want to transfer to different programs. So thank you.
So Mariah, who's next? Who's next?
Would that be me?
Mariah?
I believe is there another student that needs
Yeah,
to?
it's John Erickson.
Okay, 1 second. I'm sharing my slides out here. Okay. Can everyone see my slides?
Yes.
Okay. Hello, everyone. My name is John Erickson. I'm a PhD student at UNM in the Computer Science Department under Melanie Moses's Biological Computation Lab. And it's my pleasure today to present to you the Vulcan project, a project that I'm going to talk about today, but the acronym is the Volcano Co-Robots with Adaptive Natural Algorithms. The Biocomputation Lab is known for applying natural algorithms and algorithms kind of found in biology to computer algorithms and computer science. And if you caught the video I was playing in the corner there, what we're doing in this project is studying volcanoes with drones. So the little drone you see down there in the corner is the one you actually, if you see me on camera, is the one behind me. It's a drone we're calling the Dragonfly. So who are we? We are a multidisciplinary group of computer scientists, electrical engineers, earth and planetary scientists, and biologists, along with a whole slew of PhD students, undergrads, and I guess master's students as well. So right, we're interested in studying volcanoes, like the one you see behind the screen here. This volcano, of course, is erupting, so not a good day for the neighbors nearby. What's interesting about volcanoes is they're largely unstudied, and they're a huge threat to people that live nearby, in the fertile soil nearby volcanoes. Just as a statistic, over the past 500 years, over 250,000 people have perished because of living in proximity to volcanoes and the eruptions that occur because of that. So we're interested as an interdisciplinary group of studying these volcanoes and trying to prevent unneeded deaths and damage to surrounding areas. The way that we do that is through collecting gases and studying gases related to volcanoes, in particular CO2. The problem with CO2 is that you can't actually measure it from aerial photography or from space. So you have to fly a craft into position above the volcano. Mainly flying into the volcano is better than walking in because of volcanoes are known to be extremely rugged or dangerous terrain. So quadrotors and flying aircraft like that are just a natural go-to platform to utilize. So right, measuring CO2, it's been shown that spikes in CO2 forecast eruptions and other seismic activity. And I mentioned here, like on the slide, that the CO2 can't be measured indirectly. It has to be measured in situ or with a device in position over the volcano, collecting the gases. So as a group, we are studying these using a variety of tools, including theory that folds into simulations, and then applying that to real-world robots flying in the sky. So our goals in this project are the following: to identify the largest blooms fast, being able to find it quickly over a large amount of space is very important to us, mainly just to save time and flight time in the air. Detect plume clusters, so to know where maybe a hot spot is, or a few small plumes that might be combined into a larger plume. To estimate the plume area in total, and then to find the maximum CO2 source, also known as the maximum flux of the CO2 plume. UNM is actually staged very well for studying this because of the geological activity in the state. We're right next door to just a couple of hotspots in the area that actually have this geological activity, like the Valles Caldera, just about an hour or 2 hours out of town, also known as the Jemez to people that live here. This actually has known CO2 sources that are driven by geological activity, mainly because it's a dormant volcano, if no one knew that. But right, so UNM is very close to these hotspots, which are very attractive to us. So here we go. Here's us flying at the Valles Caldera. I hope you can make out this video. This is our Dragonfly drone, like the one you see behind me, flying above Soda Dam up in the Jemez. During this test expedition, we collected a bunch of CO2 gas and were able to pinpoint one hotspot coming out of the ground that actually correlated to some measurements we were able to take beforehand. So flying in the area, it's pretty exciting stuff. So applying computer science algorithms to drones. Okay, I have a bunch of prior work that goes into this. We as a lab study swarm robotics. Previously, we did a lot of ground-based robots. Here's a couple of pieces that are well known from our lab, namely the central place foraging algorithm, or the CPFA. This kind of dovetailed into what's known as the swarmathon. Also the golden foraging algorithm. This is an interesting piece of work because it was mainly theory in computer science that drove this work. Being able to find a hotspot in a region using the golden ratio. And a piece that I was directly involved in, our locus and mobs algorithm, being able to fly swarms of robots in either constellation or independently. And we did some analysis around that. Here's the Dragonfly drone that you saw flying in the sky. Big old battery on this puppy, mainly so that we can get about an hour flight time out of this. And on the left side, you see our laboratory grade CO2 sensor from PP Systems, which is well, we outfitted as a payload. And another little piece of video. Here's us flying the Dragonfly, doing a CO2 test against some dry ice on UNM campus here out at Johnson Field. So we were doing some tests of the system and being able to map CO2 given off by the dry ice. So we were hand flying this over just to see if we could get a reasonable reading. We were, which is pretty cool. And it seems like my time is up. So just in time, thanks for listening. This is Project Vulcan, and looking at studying CO2 above volcanoes using computer science, earth and planetary sciences, biology, and other disciplines. Thank you.
Thank you. I think Dr. Moreau is next and presenting to us.
Unmute. Hello, everyone. My name is Fernando Moreau. I'm an assistant professor in the Department of Civil Construction and Environmental Engineering. And I will be talking today about the amazing research that is happening in the School of Engineering, the Department of Civil Engineering. I wanted to thank the sponsors of the research here, and I wanted to emphasize the theme of the day. We're doing a lot of drone research. We can do a lot of outdoor monitoring. We just talked about this outdoor and safety, and I'm bringing here on the right some work from Mark Stone and Chris Lippett. They're measuring some of the nature. The one on the right is measuring ducks with drones. Ryan Webb is doing some snow, winter monitoring. Professor Susan Bogus is doing construction management and assessment using drones with Dr. Yang. And we also are interested in doing some robotics attached to the drones. This is with Los Alamos National Laboratory, where we can tap test. We're actually having a project now with the Department of Transportation. We can fly next to those bridges, tap them and listen to what they do. And maybe also the rocks that are about to fall on the mountain. We can go there and tap with our little drone and see how that happens. In my group, the Smart Management of Infrastructure Laboratory, we have multiple areas related with this LoboDrome. One of the areas that is very interesting for us is this interface with the environment. This is augmented reality. We are actually working with the Air Force Research Lab in this satellite manipulation with augmented reality. We're interested in emergency rescues with the city of Albuquerque and their fire department, how to inform and help these humans in the middle of a disaster and measure time across time, distance across time and space. I'm a civil engineer. My background is about bridges and structures, and I like to go out there and collect that data. We're working with the Department of Transportation for cracks sensing with augmented reality, with the railroads, Federal Railroad Administration, and also with our beloved tramway, where we put some sensors there and collect their behavior. We're doing some inspection, automatic inspection with low cost, efficient wireless intelligence sensors. We put them on rockets. We put them in remote locations, and we want to measure what they do for us. A lot of interest in this autonomous sensing. We're very lucky to be in Albuquerque working with the Sandia National Lab, measuring this nonlinear or linear dynamic experimentation. We're interested about measuring in a disaster like an earthquake, how things vibrate. This is in our Dana Wood structural laboratory on Centennial and a shake table where we can run some earthquakes here. And finally, with the Navy, we are interested in cyber physical systems with the cadets, the ROTC cadets in UNM. We're training them in sensors. They're building so many sensors, and they want to put them on this. This is me, by the way, with this HoloLens and the drone and the sensors, the 3D printers. And this is what we're trying to do. Go out there and bring this technology to do measurements for the things that are happening out there. I will end with this picture before Roya tell us more about this. Very big bridges that we have out there to measure and monitor. This is part of the team here. They are so young and so handsome. So how do we go to this very big bridge and measure the data? So maybe Roya can take over here and share her screen. Thank you so much.
Thank you. Good afternoon, everyone. I'm Roya, and I'm very glad to present here today. And today I'm going to cover two things in my presentation. First of all, I will cover this giant UAV system that we created in our lab, and then I will cover that what LoboDrome facility could provide for our project. So this is the ASCE report card about the condition of the railroad bridges in infrastructure in US. And as you see, $3.6 trillion is the cost of improvement this infrastructure. And this is a very big amount of money. So we have to prioritize our decisions. And railroad bridges is as a fraction of this infrastructure system needs good taken care of. And railroad bridge managers are interested in displacement values. So what we do, we have a bridge here and the train is crossing over that. This bridge is vibrating and we have a UAS or drone right there equipped with sensors. Basically in this project, we use a laser shooting to the surface and finding the displacement. But as you expect, the bridge is moving, the UAV is moving. So these signals is not going to give us the very accurate displacement. Then what we do, we add a camera to the drone and just find the corrected data from the laser. And we had to develop a hardware and software system and algorithm. Basically, this is working with camera algorithm. I have to just give a algorithm in a nutshell. Our algorithm is working in two phases. First is using a computer vision algorithm called pinhole camera model for translational motion correction. Then we're finding Euler angles and correct for angle or rotational errors that was induced on the signal. And beside the algorithm, we have to develop a hardware system. And this is the gigantic hardware system that we created. We use DJI 600 Pro and like lots of sensors, and we put together on the drone to enable displacement measurement. And we fly in the Balloon Fiesta Park, and we were able to collect data without any problem or accident, and we get them. After collecting the data, we just use the algorithm to estimate the displacement of the board. Here is the displacement estimation versus the real data collected by LVDT. We were able to collect displacement within millimeter range. And more details or more results about this project will be available in the papers. We've submitted very great papers to good journals, and I think that they will be available soon. So that is the outcome, that is the result. But like things have preparations and backstage. I want to show you, I'm moving to possibilities that LoboDrome could bring for us. So what it takes for us. Here is our laboratory, Center for Advanced Research Computing in Karsi in UNM. We thank Dr. Bridge for this facility that we're developing our algorithm there. But we are using with drones, and we're creating algorithms for drones. So we need to fly, and we cannot fly indoor. So what I came up at first, like when we put together the sensor system, I put this drone on the box and just try to pretend, okay, I'm like collecting some data, but the drone should move. The drone should fly, and we cannot do it indoor. But actually, we did somehow. I'll show you a secret. Don't share it with the manager or Karsi. So we have this great collaborator. He's super strong man. He just had to lift it because the drone should be moving, you know. Then this guy is just pretend like the UAV is moving just before going out to the field. We could collect some data this way. And I really thank and acknowledge my friend. And then this is not the old story. We have to get prepared for outdoor. And believe me, like California preparation, like trip preparation takes you less, because like this needs, we had to check that if there is an event going on in Balloon Fiesta, or if there is a visitor there, or how is the weather condition for like flies, and is there any, like we had to strict to time schedule to just follow the timeline. And we had to carry all the test bed to the truck and to the Balloon Fiesta. And yeah, and also we had to create a whole lab facility out there, like in Balloon Fiesta. We didn't have power generators there. We have to take it with ourselves. So this lead me to just, build my own portable laboratory, and like ask my assistants like to go there with me in every experiment. And yeah, we're happy that we have the Balloon Fiesta Park close here, but having a LoboDrome facility like in campus will help us to fly the UAV and develop algorithms and make the impossible things possible. And I really thank you for your time, and I hope you enjoy the presentation. Thank you.
Thank you, Roya. I believe now we will hear from Professor Sun.
Hey, good afternoon, everyone. Can you see my screen?
Yes.
Okay. So good afternoon, everyone. I am Xiang Sun. I'm an assistant professor in the Department of Electrical and Computer Engineering at the University of New Mexico. And it's my pleasure to present our work, recent work in this event. So one of our current research topic is tunable free space optical communications. So first, let me briefly introduce what is FSO. So basically, FSO is a type of wireless communications that uses optical beams in free space to wirelessly transmit data. So as compared to the traditional radio frequency communications, FSO can achieve a very high data rate over a longer distance. And FSO has widely been used in the ground to satellite and satellite to satellite communications, whereas radio frequency communications is not quite suitable due to the long distance between the source and the destination nodes. So recently, FSO has also been applied in the cellular networks to speed up the data transferring process. So for example, the FSO can be used in the backhaul link between a cellular tower and a gateway. So with respect to the tunable FSO-based serial backhaul networks, the term tunable means that FSO transceiver can adjust its position to receive optical beams from other different FSO transceivers. So for example here, a gateway is equipped with a tunable FSO transceiver to receive data from different three different cellular towers which are geographically distributed. So we have implemented this testbed of the tunable FSO communications in our smart edge computing and networking lab. So in this testbed, we have one FSO receiver here and two FSO transmitter, and all of them are connected to the computer. So the FSO receiver is mounted on a gimbal, which is controlled by a programmable controller. So the FSO receiver can adjust its position accordingly. So the wavelength of optical beam for carrying the data is 1550 nanometer, and the transmission power of the optical beam ranges between -1 to 4 dBm. So this is a demo of our tunable FSO test bed. So let's take a look. So we can see that the FSO receiver is switching back and forth to receive data sending from the two FSO transmitters. So these three figures shows the data rate of the two FSO transmitters and the data rate of the FSO receiver. Also, we have developed a scheduling algorithm to determine how long time each link, FSO link, should be maintained based on the traffic load of different transmitters. So for example, if the transmitter 1 has a higher traffic load than the transmitter 2, then the tunable FSO receiver should maintain this link, the FSO link, between transmitter 1 and the receiver longer than the transmitter 2 and the receiver. And we can see that the average data rate of the receiver is longer than, it's more than 4 gigabits per second, which means that you can transmit a very high, very high data rate in a very few seconds. Like if you want to transmit a high quality video, which you can transmit within a couple of seconds. So the FSO can provide a very high link capacity of a long distance. So in order to reap this benefit, we were applying this FSO in drone-assisted mobile access network. So in a drone-assisted mobile network, a drone is equipped with a small cell base station, and the drone can be quickly deployed and over some sporadic hotspot area, like the traffic jam area, concert, football stadium, to provide very high-speed wireless connections to the mobile users. All the drone can be placed over like a disaster strike area to offer the emergency wireless communications for the victim. So in our drone-assisted, drone-based, in our FSO-based drone-assisted mobile access network, the data streams are transmitted from a cellular tower to a drone over the FSO link with extremely high data rate. So the drone then can convert the received optical signal into the RF signal and then transmit them to the mobile users. So there are several research issues in the drone-based in the FSO-based drone-assisted mobile access networks, which we are currently working on. So first is how do we optimize the deployment and the trajectory of a drone to maximize the network throughput? So the drone deployment and the trajectory of depends on many factors, such as the distribution of the mobile users and the location of this cellular tower. Second, how do we optimize the setup of the FSO link? For example, we are currently working on how to derive the optimal divergence angle of this optical beam such that the receive optical power at the drone can be maximized and the link outage probability can be minimized. Third, since the FSO is using a very narrow optical beam to carry the data, so any beam misalignment between a cellular tower and a drone could break the FSO link. So we have to develop a cost-effective acquisition, tracking, and pointing ATP system to accurately align an optical beam in order to ensure the optical beam can be received by the moving drone. So this is a demo of acquisition tracking and the position system, which achieved a coarse grain tracking. Basically, there's a camera which is mounted on this ground gimbal. So the camera is used to capture, identify, and calculate the moving direction of the drone. Then the results are used to control the movement of this gimbal. So let's take a look. So we can see that as the drone moving around, the position of the gimbal is also adjusted accordingly to guarantee that the drone can always be in the camera's view. So in the future, we're going to test the performance of the FSO link between a cellular tower and a drone in an outdoor environment where the atmospheric turbulence, maybe the mechanical vibration of a drone may degrade the performance of a FSO link. Also, we are going to evaluate how the deployment and the trajectory of the drone affects the network throughput in an outdoor environment. And I believe this LoboDrome project could make this research activity happen at the UNL. Thank you.
Thank you, Professor Sun. I believe we'll be hearing from Dr. Moreau again.
Everybody hear me? Yes.
Yes.
So let me switch this. So to wrap up this very nice presentation, this is a view of the building of Centennial. Thank you for the Dean for letting us build the LoboDrome. We are showing what we have here in mind. And this is from the top. And this is kind of the different presenters today show a lot of technology and a lot of development of algorithms. We need some level of space to develop these algorithms. In my class on steel design, I gave a competition to design a LoboDrome, and I have some designs. So the best student of today will win a drone. They will send you a survey. So write down your number and see the one that wins. It's gonna go very fast. 10 seconds per slide, pay attention. Number one, this is 2019 design from Xin Yuan. It's a mosquito net where she has some kind of a net on the walls, net on the roof, and that's what she proposed. Number two, the net design, this is from Nicole Trujillo and Selena Dam, kind of a grill around the net so you can fly in safely, and you can see their beautiful finite element that they designed for their net. Good job. Number three, Twin Arches design by Angel Padilla. She has kind of this double dome, beautiful concept. Great job. Number four, the Spider Net by Patient Ravi. She has this Spider-Man, Spider-Woman vision on the top. I really like it. Number five, Pyramid design from Jenny Robertson and Lynette Torres. Very creative, the Louvre Museum in Paris. Rocket design, Roland Garros, Avinash Upreti and Marielle Jones from that kind of non-symmetric roof. The grill design by Dominic Thompson is kind of that vision of having on the top, it looks, that's the Centennial from the top. Number eight, Sea Rising design by Ben Gallegos and Carl Avedon, and they had this Zia rising concept on the roof, and they were thinking maybe putting some robots closing and opening that. Saika Mustari Susmati Nest at Centennial Design. Obviously, she likes a structure, so she has this nice 4 trusses, and then we will have the net on top. Number 10, a barrel design from Lucas Bierek. Kind of, you see, like it looks like a little barrel, very curvilinear shape, and similar the dome design by Dominic Thompson. Number 11. So 1, 2, 3, 4. Pick your number. They're going to send you a survey to choose, so you can vote for them, and then they will be giving a drone because of your choice. So I will let this another 5-10 seconds. You can check the video later. Okay, make your number and reply to the survey that you will receive for this student competition. I want to invite everyone to contact Leslie Armel from the UNM Foundation for any questions, inquiries, or any ways that you can support the LoboDrome. We want to hear from you. Thank you very much, Mariah.
Wow, thank you. So thank you, all of you. Well, I want to thank all of you for sharing all of your incredible work with everyone and your plans for the new LoboDrome facility. So we will now start the question and answer portion. So again, you can use the chat function. It's the little symbol at the bottom that looks like a little message. And we do have some questions prepared already. The first one is, are all drones equal, or is there a preferred drone?
Maybe I can try to answer the question. I don't think they are all equal, right? And the application will define what type of drone you are looking for. For instance, in the volcano case, you may need to have a rotorcraft type of vehicle in order to have, I think, measurements, right? Measurements of the CO2 or so. But then, if you need to cover a extended area or extensive area, you may prefer to have a fixed wing. So I think the application is going to define what type of drone. But I think John may comment because John is the expert. John Erickson.
That's pretty accurate. So we actually designed. We were looking at a bunch of different drones on the market, and we settled on designing our own mainly because we could answer the requirements directly. And the requirements we had were we needed to be able to hike with our drone up the side of a volcano. So one thing I didn't cover in the talk was we have a foldable design that fits in a backpack. But right, there's all sorts of different drones out there that are meant for photography or videography, which are maybe a little more cost efficient or stable for that sort of those sort of requirements, or for flying indoors. Our drones don't fly indoors; they need a GPS signal. So,
all right.
Yeah. So from my point of view, I think the drones could be like, in my research, I prefer to use the drones with higher payload capacity, such that they can like carry some FSO transceivers, wireless transceivers, and some other things. So also the drones should have a long lifetime. They can last they can stay in the air for a long time. So I think different research topic will have, or applications will have their own preferable drones.
Great, thank you. Our next question, what makes UNM the right place for you to do your research?
The dean. I think I'll tell you one thing in my personal experience. I like to do a lot of outdoor experiments, and in other parts of the country, we don't have as much nice weather like we have here. Roya was showing her drone on the Balloon Fiesta. We have the monsoon season, and that was the worst thing that could happen, monsoon season, and that happens, at a certain time of the day on these months of the year. I mean, beautiful weather for flying outdoors is very difficult to find this elsewhere. That was, in my case, why I chose to come to UNM. I knew I could be outdoors with the sensors and the drones not common in other parts of they cannot do this.
If I can add something, there are so many aspects that make UNM an ideal place to do research and to develop your career. I can comment in one aspect, for instance, the proximity with the national labs. In my opinion, is fantastic. I think having Sandia, AFRL, Los Alamos is not here, right, but they are close enough. And so definitely, I think having the national labs nearby as a neighbors, right, it's a like 10-minute drive maybe, is in my opinion, facilitates the collaboration. I am really happy and really grateful for the contacts that I have about Sandia and Air Force. That, I mean, if I were in some other place, I may be able to have some research, but I don't think it's going to be as let's say as efficient or so the communication and the proximity with national labs is for me is a major factor.
Great, thank you. We have a question from Doug. They ask, is flight in the stadium permissible?
Which stadium?
Yeah, UNM, the football stadium, I guess.
Possibly John may know all those details, right, John?
So what we've flown on what Johnson Field. That's mainly a soccer field, I believe. Or we've actually taken advantage of the RC parks in town. So there's like 3 different parks that are dedicated to radio control aircraft. One's actually near my house, which makes it convenient for me. So we haven't flown in the football stadium specifically.
All right.
The answer would be no, because it's too close to the airport, and they won't like us there. They won't. I won't go. I mean, you shouldn't fly there. So that's why we go to the Balloon Fiesta. It's far enough. We had the pilot. So you need that, but the distance that close to the airport. Please don't.
Great.
Every time we've flown in Johnson Field, we've had to file a flight clearance to be able to do so.
Oh, wow. So Akil asks, you mentioned a LoboDrome facility. I'm not sure if you want to maybe like just specify or kind of, sorry, go ahead.
What was the question?
What was the question? Sorry, Maria.
Yeah.
Oh, no, you're fine. I think it's about the LoboDrome facility. Maybe just hearing like a little more about that. Because I think it was probably talked about briefly.
I'm not sure if maybe Leslie, you want to say something about additional details. We can keep talking about the technicalities and the need or so, but maybe some additional ways that perhaps this audience can help us out. Or
I don't know if Leslie's here. Do you want me to say something? Basically, we are trying to create this facility for research, for also, education. And without doing this, it becomes very difficult, very limited, to what we can do. And certainly our goal as the School of Engineering is to do a fundraiser to raise enough funds to build it. And this facility, it's called the LoboDrome. It's M-E, not the LoboDrome. So it's like we're going to have competitions, we're going to have races, we're going to have amazing things going on there. And it's going to be all enclosed. We don't want to bother anyone. We don't want to have issues with the airport personnel and the folks there. So it's going to happen. It's just a matter of how fast we're going to raise the funds.
All right, thank you. Our next question is from Doug. He asks if Arduino is going to be used in your designs.
Arduino is the question? Arduino?
Yeah.
Okay.
used in your design?
I wonder if maybe Isaac or Mark would like to comment. So I would like to give opportunity to the students.
Roya.
Roya too, of course.
I can say something really quick. So we use several things in our design. So we were using an NVIDIA Jetson Xavier. We used a NVIDIA Jetson TX2. We've used Odroids and several other things. I mean, it just depends on your application. You know, if you want performance machine learning, in machine learning stuff, you probably want to use something NVIDIA. If you want something with more cores, you know, like an Odroid is better. So it just depends on your application.
Yeah, my comment for that question is that we got the drone and we had to design our sensors, our data acquisition system. And we basically needed 2 data acquisition systems for the drone that we designed for the laser and the accelerometer. And we use Arduino and we transferred the data with XP board as a data acquisition system. And this helped us to remove the tether and just equip the UAV with the sensors and fly without any wire problems and sending the data wirelessly.
Great, thank you. Our next question is from Nicholas. They ask, for the volcano drone, is the CO2 sensor taking into account the air displacement that props put out? Does that matter when measuring CO2?
I think the short answer there is yes, but mainly what happens around the drone is there's a mixing effect of the ambient CO2. So we're not getting maybe the highest CO2 spike from the ground that you may be, you know, wanting to measure. But, you know, then again, I don't think we're looking for that. We're looking for ambient CO2. And so really the answer is it produces, the rotor wash produces a mixing effect around the drone that it's very hard to get outside of. So we could hang a hose off to the side or very far down below, but that changes a lot of different things like the flight dynamics that we have to worry about. So.
Great, thank you, John. So we have one from Gabriel next. They say, hello, thank you for the presentation. And can we know the estimated flight volume for the UAVs?
Weight?
The estimated flight volume for the UAVs?
Yeah.
I don't know the volume. I think so from our perspective, we're worried about the weight because we have different sensors that we want to bring to the bridge or to collect, or maybe the hammer to tap on the bridge. So that's gonna add some weight. Then it's more power. So the powers are gonna add more weight, and then the weight determines the drone that you can use. So more than volume, it was more of a payload limitation that we consider for the capability of the drone to carry something extra on addition.
All right, thank you.
It's an interesting question. It's an intriguing question. I don't have a good answer for that. I guess it's because we are in the basement, so we say, well, that is our volume, right? So we cannot move more. But if we have the LoboDrome, possibly we can start thinking, okay, well, more in terms of those type of variables, right? But I think I appreciate the question. It's something that perhaps we should give some thought.
Clarify, yeah.
Great, thank you. Our next question is from Mary. She asks, the drone facility design seemed to utilize the Centennial Building courtyard. Is that the only location being considered?
Rafael, you want me to answer that? Sean?
Go ahead, Fernando.
Sean hasn't talked. Sean, don't you want to talk?
Go ahead, Rafael. You are the leader of this project, right?
So basically, the benefit of Centennial is that the dean can take a look in what we do, and he likes that. but Centennial Centennial has the hallways. We have 3 stories where the students are taking classes. They are there. Very nice windows. It's like going to an aquarium. You see the drones near you. We have the access, even from the roof, we could have some safety and allow to fix the drone from the top. And also we have all the energy, power, computer contact with our supercomputers. Everything is on Centennial. So that's the benefit from our perspective, that is, we have something that no one else has already.
Yeah. It's also centralized. You got all the departments that are involved with this type of research, they're all there. So instead of going anywhere, if you were to go anywhere outside that Centennial, it would be too far from at least one department. So I think this is the ideal place. And plus, at this point, that space is not utilized very much. Maybe only twice a year we have some events. So it's ideal.
All right, great. Thank you, guys. Let's see, we have one from Dawn. They ask, is there any research in battery life? I had one explode in flight. And are you working with video app development?
So we have the concern on the battery life, and that's a very important topic, because we imagine we have a train crossing the bridge for you know, there are different parts of the bridge are carrying these cameras. I mean, ask about the camera app. So we're using, I think everybody's interested in computer vision on the university with drones. So that is a very, very hot topic these days. That's very, very common, right?
I think the battery is so critical, really. So it's well, one of the most critical aspects, right, for a drone. So without a battery, you have a failing battery, the mission is compromised. So we try to use, I think, we try to basically be careful, use the right equipment in terms of charging and discharging the batteries and so on. Try to be very, again, careful and follow the best practices. However, trying to basically, I think maybe we don't have the expertise in order to answer questions of how we can improve batteries, right? So possibly that could be in the different departments, maybe in chemical engineering. We know that out there is a competition, right? The Tesla and other companies, big companies, about batteries. So we are hoping to get some safe equipment, and we are careful to use the equipment properly. If I can answer the question in a different, or maybe try to talk about a little bit of the research aspects of batteries of power. One thing that we are considering in our research is that when in our own algorithms, when you deploy a team of aerial vehicles, the algorithms, they should consider the battery or the power as a constraint. So you want to be, let's say, you want to optimize, you want to minimize the power or the battery usage in order to, well, in addition to accomplish your mission. So sometimes it's very common that people do not consider that the drones, they have a limited battery. So you could have a very efficient algorithm. You could capture, let's see, in our case of capturing incoming drones, you could capture the drones very fast, if you will, but you do not constrain the optimization problem. So that is not going to work well in practice, right? So I think in the different applications that we have seen here, like the volcano monitoring, in our case, the counter drones, in case of Professor Sun, the optical communication, all of them basically should also optimize power and energy consumption. yeah, but I think we understand the importance of that, and at this point we're trying basically to to follow the best practices in terms of safety.
All right, great, thank you. Unfortunately, we've met our time, and I just want to say thank you for everybody for joining us today. Thank you to all the speakers for sharing this exciting research with all of us, and thank you to all the guests who are here. Our next talk in the Engineering in Action series will be on December 4th at 3 p.m. and this will focus on new directions in artificial intelligence. So we look forward to seeing you again, and thank you again for joining us, and go Lobos.